In this module, we will look at the power plant and propellers of the ATR. We will start out with an overview of the engine and propellers. Next, we will look at the engine controls and the feathering system. Finally, we will review the fuel control system. Two Pratt & Whitney PW127F series free turbine turboprop engines are installed on the airplane. These engines develop a normal takeoff power rating of 2,475 shaft horsepower. An automatic power-up trim feature allows either engine to develop up to 2,750 shaft horsepower for brief periods following an opposite engine failure during takeoff. The engine features a two-spool gas generator consisting of a low-pressure and high-pressure centrifugal compressor, each driven independently by single-stage axial turbines on coaxial shafts. A two-stage free power turbine, aft of the compressor turbines, drives the propeller via a third shaft, running forward through the low-pressure compressor rotor to a propeller reduction gearbox at the front of the engine. Air enters the engine through an S-shaped duct. The design of the duct is such that a uniform inlet flow is supplied to the compressors. The curvature has two purposes. The first purpose of the curvature is to remove foreign objects that may be ingested. Separation is accomplished by inertia. Since air has less mass, it can easily make the turn into the engine, whereas the inertia of heavier particles or contaminants will carry them overboard. The second purpose is to divide the airflow into a primary flow for the engine and a secondary flow for the oil cooler. Airflow used to cool the oil cooler is controlled by an oil cooler flap, which is positioned automatically. An exhaust pipe is connected to the engine tailpipe and ducts engine exhaust to the rear of the nacelle. An accessory gearbox is driven by the high-pressure compressor shaft to operate the engine-driven fuel pump, an oil pump, and the DC starter generator. The accessory gearbox is mounted at the top of the engine. For engine starting, the starter generator drives the gearbox to accelerate the high-pressure rotor to the necessary speed. The high-pressure spool is used for starting because it is smaller and lighter weight, and therefore easier to spin up. Other accessories are driven by the propeller reduction gearbox. These include the 115-volt AC wild generator, the propeller valve module, or PVM, a high-pressure oil pump, a propeller overspeed governor, and the fuel-cooled oil cooler. In addition, the propeller reduction gearbox houses the electric auxiliary feather pump. The right engine reduction gearbox also includes a propeller brake. The propeller is a Hamilton Standard 568F with 6 blades, a feathering, and a reversible unit. This propeller is constructed using all composite blades, a novel and unusual design feature when it was first introduced. The blades of the propellers are all composite counterweighted, and the spinner is made out of aluminum. The propeller is driven by the free power turbine through a reduction gearbox. This means it is not connected to the other two spools. The turbine is spun by exhaust gases alone. Propeller pitch is hydromechanically controlled by a propeller valve module, or PVM. The PVM is installed on the reduction gearbox. Propeller pitch is changed by oil pressure that is supplied by a feathering pump. Oil is supplied by the engine's lubricating system. This oil pressure then adjusts the associated propeller pitch. Metered oil pressure is dumped, which allows supply pressure to feather the propeller. If the propeller is feathered by the ATPCS system, or by a fire handle, a valve is electrically actuated to dump the metered oil pressure, thereby allowing the propeller to feather. Each engine nacelle incorporates a Propeller Electronic Control Unit, or PEC. The PECs control their associated propeller valve module, as well as the synchronization of the phases of the propellers. Each PEC controls the pitch change mechanism of each propeller through one of two channels. In the event one channel fails, the backup channel will take over the control functions. The PEC calculates the correct propeller speed using altitude and airspeed data, as well as information from NP sensors. The EEC interfaces with the PEC in this control function. A Propeller Interface Unit, or PIU, provides an interface between the engine controls in the flight deck and the associated propeller electronic control. There are two PIUs that are installed in the electronic rack. The propeller valve module provides for governed constant speed operation, power lever control beta range from idle to full reverse, propeller feathering, synchrophasing, and low propeller pitch angle protection. The PVM will also provide propeller over speed protection. The propeller is discussed in a separate module. The PVM consists of an electrohydraulic valve, a protection valve, a feather solenoid, and a rotary variable differential transducer. The electrohydraulic valve meters oil to the pitch change actuator and allows a normal feathering of the propeller. The protection valve is part of the overspeed, low pitch protection, and backup feathering systems. The feather solenoid acts as a backup to the electrohydraulic valve. The rotary variable differential transducer adjusts and confirms the power lever angle. A propeller brake is installed on the counter shaft of the right engine reduction gear box. When the propeller brake is engaged, the propeller and the power turbine stop. This condition is known as the hotel mode. In this situation, the high-pressure spool drives the right DC generator, and bleed air pressure is available downstream of the high-pressure compressor. This air can then be used to supply both packs. Operation of the propeller brake requires that blue hydraulic pressure be available for engagement or disengagement. Engagement of the propeller brake can only be done when the aircraft is on the ground and the prop brake switch on the overhead panel is in the on position. In addition, the gust lock must be engaged and the right condition lever must be in the feather or fuel shutoff position. When all the propeller brake engagement parameters are satisfied, the ready light illuminates green on the overhead panel. This light must be illuminated prior to engaging the propeller brake. The ready light may remain illuminated for up to 15 seconds after engagement of the propeller brake. The propeller brake light illuminates blue on the overhead panel when the propeller brake is fully locked. There's also a propeller brake light that illuminates on the memo panel as well. An engine electronic control unit, or EEC, controls the flow of fuel through the hydromechanical unit by means of a stepper motor. This controls a torque motor based on ambient conditions, the position of the associated power lever, the selected power management mode, and the position of the bleed valves. The stepper motor then adjusts the fuel flow commanded by the HMU. Based on these conditions, the hydromechanical unit, or HMU, will deliver the fuel flow required to obtain the commanded compressor rotation speed. This value is called NH. The engine EEC receives power lever angle information, the mode selected on the power management panel, the position status of the bleed air valves, engine parameters, and air data information. Based on this information, the EEC uses this information to calculate a new power setting and supplies correction signals to the HMU stepper motor. This system allows optimum fuel scheduling under varying engine, ambient, and operating conditions. It also reduces pilot control and monitoring. Engine fuel control may be selected to on for control under engine electronic control or off. In the off position, the HMU controls the NH based on the position of the associated power lever. An EEC mode switch, located on the engine control panel, allows for selection in either normal, on mode, or manual reversionary condition. When fuel control is on and there is an EEC failure, the associated EEC fault light will illuminate, and the fuel scheduling is fixed at the point the EEC fault occurred. If the fault occurred with the power lever above 52 degrees, the EEC fault light will flash, and the movement of the affected power lever will not result in a change of power. It should be noted that deselection of the affected EEC is prohibited while the fault light is flashing. The power lever should be moved below 52 degrees, at which point the EEC fault light illuminates steady. Once below 52 degrees power lever angle, the power lever is able to control the engine, and the affected EEC can be selected to off. When the fault light illuminates, the engine light illuminates, both master caution lights will flash, and a single chime will sound. Selection of the EEC1 or EEC2 push button to off will cause the off caption to illuminate in the push button. The fuel control system will be under HMU control. The HMU will only control the NH based on the associated power lever angle. Placing an EEC push button to the on position will cause the associated fuel control system to revert to EEC control. When off is selected, propeller underspeed control is lost at low power. Manual fuel scheduling is controlled by power lever angle setting. The PLA settings provide fuel demands and control the propeller blade angle in the beta range. Flight beta occurs below 62 degrees PLA, and ground beta between the flight idle and ground idle stops. The condition lever angle settings provide for fuel on-off control through a shut-off valve in the HMU and manual selection of the propeller to feather. The engine power control can operate in one of two modes called control laws. These laws are the base law and the top law. Base law is used when the associated EEC is inoperative. In this case, fuel control is relative to power lever angle. The power lever is connected to the HMU and the PVM through cables and rods. In the base law mode, changes in ambient conditions will result in a change of NH, so it is important to remember that you'll need to adjust the power lever angle in order to maintain the maximum engine torque. When operating in the base law mode, there will be a loss of propeller underspeed control at low power. Normally in the flight idle to ground idle range, engine torque is minimal, so the EEC schedules only enough fuel to prevent NP from going below 70.8% NP. This is the underspeed governing function of the EEC. This mode is cancelled when the propellers are put in feather or if the EEC is turned off. The top law operates when the EEC is on. This law will provide NH overspeed protection. The top law will command a specific engine power based on the rating selected on the power management panel, the associated power lever angle, the flight conditions, and the position of the bleed air valves. The top law includes an NH backup law, which is activated at low power settings in the event of an engine torque control failure or in the hotel mode. The top law provides minimum propeller speed control on the ground and at low power settings, and provides automatic up-trimmed takeoff power in the event of an engine failure on takeoff. In addition, the top law controls the modulation of the handling bleed valve to optimize low-pressure compressor operation. There are 3 modes of propeller speed governing. These modes are blade angle governing, fuel governing, and the transition mode. Blade angle governing is the normal mode of governing while the aircraft is in flight. In this mode, the propeller valve module adjusts the propeller pitch so as to maintain a constant propeller speed. This mode is available regardless of the status of the associated EEC. In the blade governing mode, the power management selector commands the propeller speed through the propeller electronic control unit, and the power levers command power. Fuel governing is a ground governing speed used at low speed and low power. In this mode, the EEC automatically increases fuel flow so as to maintain a minimum propeller speed. The fuel governing mode is available when the associated condition lever is in the auto position. The fuel governing mode is also not available when the associated EEC is off or when the associated propeller is feathered. With the EEC off, there is no propeller underspeed protection while in the fuel governing mode. The transition mode is active when the aircraft is on the ground or in flight at low power settings and low speed. While in the transition mode, the propeller speed will be between 70.8% and 100%. We will now look at the engine controls. The power levers are mechanically connected to the hydromechanical unit and the propeller valve module. The 2 power levers, marked 1 and 2, control engine speed in the forward power range, and engine speed and propeller blade angle in the idle and into the reverse beta range. For normal flight operation in the forward thrust range, propeller blade angle is controlled by a propeller valve module. The propeller valve module, or PVM, hydromechanically controls the propeller pitch, which regulates propeller speed in response to power settings. This governing function is available regardless of the status of the associated EEC. Engine power is controlled by the power lever. As the power levers are retarded to flight idle, with the condition levers at auto, the PVM reduces blade angle as it attempts to maintain the selected propeller RPM. As blade angle reduces to a point slightly above the flight idle setting, the power lever acquires direct blade angle control. At flight idle, the propeller blade angle decreases further. If the propeller speed drops below 70.8%, the EEC will increase fuel flow so as to maintain a propeller speed of 70.8%. For descriptive reasons, the beta range of power lever movement above flight idle is designated flight beta, and the beta range between flight idle and max reverse is called ground beta. A flight idle gate prevents unintentional movement into the ground beta region during flight. The gate is automatically unlocked as soon as one landing gear shock absorber is compressed. Once unlocked, the power lever can be moved to ground idle and reverse. If the gate fails to retract automatically, the idle gate fail light illuminates and the CCAS is activated. In this situation, the gate can be retracted by pulling the idle gate lever located on the center pedestal. Once pulled, an amber band will be visible. In the flight idle to ground idle range, the propeller blade angle is further decreased by pulling on triggers located under the power lever knobs. This allows the pilot to pull the handles out of the flight idle notch down to ground idle and into the reverse range. The reverse range requires the pilot to overcome a spring force, which attempts to return the power levers back to the ground idle position. Further power lever movement aft moves the blades into reverse until the power levers reach max reverse. Releasing the power levers will allow the spring rod to return the power levers back to the ground idle position. While in beta range, the propeller valve module regulates power to provide propeller underspeed governing in the flight idle, ground idle range. While in the reverse thrust range, the HMU and the PVM also regulate power and propeller speed, proportional to the amount of reverse blade angle selected with the power lever. The two condition levers, located adjacent to the power levers and marked 1 and 2, set propeller RPM in the forward thrust range and provide manual propeller feathering and fuel on-off control for engine start and shutdown. Each condition lever provides input to the PVM and HMU of the associated engine. When in the forward thrust constant speed range, the position of the condition lever sets propeller RPM through input to the governor in the PVM. At 100% override, propeller RPM is governed at approximately 1200 RPM. Moving the lever aft to the auto position controls the propeller speed through the power management selector position. Moving the condition lever to feather feathers the propeller and disables the propeller underspeed governing to allow ground idle engine operation in feather. Moving the lever to fuel shutoff cuts off all fuel flow to the engine. Lift gates at the auto and feather positions prevent unintentional movement of the condition levers from auto to feather and from feather to fuel shutoff. A trigger must be pulled in order to move the condition levers to these positions. The trigger must also be pulled in order to travel from fuel shutoff to feather and from feather to auto. The Automatic Takeoff Power Control System, or ATPCS, provides automatic propeller feathering on the failed engine and non-affected engine power uptrim following an engine failure during takeoff. The ATPCS system is armed under the following conditions. The power management selector is set to takeoff. The ATPCS push button is in. Both power levers are above 49 degrees PLA. Both torques are above 46%, and the aircraft is on the ground. Therefore, if one engine has been shut down in flight, the ATPCS system can't auto-feather the remaining good engine. In flight, the auto-feather function will still be armed if the above conditions are met, but there will be no uptrim logic once the power management selector has been taken out of the takeoff position. Each EEC features a power uptrim mode during takeoff, which automatically increases power output from the non-affected engine up to 10% in response to an MFC auto-feather command. The maximum permitted shaft horsepower is 2,750. Auto-feathering is handled by the Auto-Feathering Unit, or AFU. The AFU supplies torque indications to the flight deck indicators, the Flight Data Acquisition Unit, and to the MFC. The MFC handles the auto-feathering and uptrim logic. When the MFC commands a propeller to feather, it signals the affected feather solenoid and the associated feathering electrical pump to feather the affected propeller. In addition, it commands the operating engine EEC to increase the non-affected engine's power output. The power uptrim occurs 2.15 seconds prior to propeller auto-feather and is indicated by an uptrim advisory light on the engine instrument panel. When the EEC of the non-affected engine receives the uptrim signal, the uptrim light is illuminated, and the fuel schedule increases above that selected by the power lever to provide power uptrim. Prior to initiating propeller autofeather of the affected engine, an NP underspeed fuel governing cancel signal is received by the EEC. This fuel governing cancel signal permits the feathering propeller to decrease RPM through an underspeed condition to a feather blade angle. This fuel governing cancel signal permits the feathering propeller to decrease RPM through an underspeed condition to a feather blade angle. Once feathered, the auto-feather system on the operating engine is inhibited and the ATPCS arm light extinguishes. In addition, the operating engine bleed air valve is automatically closed. Following an engine failure in flight, the ATPCS is disabled by selecting any position other than takeoff on the power management panel, selecting the ATPCS push button to off, or retarding both power levers. The uptrim light extinguishes and the EEC returns its associated engine to the original power setting. If the crew decides to restart the failed engine, the propeller can be unfeathered only by selecting the MCT position on the power management panel after the engine has been started. The ATPCS is armed on the ground when the takeoff position is selected on the power management panel, and the ATPCS push button is pressed in. In addition, both power levers must be above 49 degrees PLA, and the torque on both engines must be above 46%. Once the system is armed, the arm light illuminates. If the ATPCS push button is pressed in while the aircraft is in flight, only the auto-feather system is enabled. The automatic power uptrim mode is inoperative. This concludes the engine and propeller control module.